Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 15, 2025, just yesterday. The big idea is a plugin module called PhysMaster that learns a physical representation with reinforcement learning and human feedback, using direct preference optimization, guiding image to video generators to follow physics, with semantic adherence 0.67 and physical common sense 0.40. The paper is titled PhysMaster, Mastering Physical Representation for Video Generation via Reinforcement Learning. And as we will see later, the implications for controllable video dynamics are significant. Beyond that, the method uses a three-stage recipe that fine-tunes the generator and then the PhysEncoder, reaches IOU 0.468 on a free-fall proxy task, and runs efficiently at about 26 seconds per 5-second video on one A800 GPU. Also, the authors shared the official GitHub. You'll find a concise README with a TLDR and method overview, an assets folder with gallery videos for comparisons and ablations, and update notes pointing to the project page and RX4. It looks like demos and documentation are up, while full training code isn't obvious yet. Alright, Figure 1 presents the end-to-end setup that injects a learned physical signal into an image-to-video generator so motions follow real physics. Direct preference optimization means the model learns from paired videos where a preferred clip should be more likely than a rejected one. The left side illustrates preference data construction with positive and negative generations. The right pipeline shows PhysEncoder features fused with visual and text embeddings, transformed, then decoded into a video with feedback. Well, Figure 2 compares generated freefall videos across methods and shows that the proposed approach preserves object shape and follows realistic paths. A proxy task means a simplified setup that stands in for a broader goal, so success here signals better physical reasoning. The left block keeps shapes crisp and landings consistent. The middle block from PySA drifts in shape. The right block from PhysGen often misplaces objects during motion. So, Figure 2 showed visual wins. Table 1 quantifies how each training stage improves physics. The table compares supervised fine-tuning, direct preference optimization on the generator, and direct preference optimization on the PhysEncoder across seen and unseen splits. Stage 3 delivers the best average IOU at about 0.144, which reflects stronger shape consistency. It also yields the lowest average L2, near 0.047, so trajectories align better with ground truth. So Table 3 compares models on open-world data and shows that this approach leads in both accuracy and speed. Physical common sense, which scores whether motions obey everyday physics, peaks at 0.40 for the final model. Semantic adherence reaches 0.67, matching the strongest competitor while staying faithful to prompts. Inference takes 26 seconds for a 5-second clip, so generation is practical for everyday use. For comparison, WISA needs 220 seconds. Alright, 2 takeaways stand out. A plug-in PhysEncoder, trained with direct preference optimization and human feedback, injects physics into image-to-video generation, and the 3-stage recipe measurably boosts realism, with semantic adherence near 67% and physical common sense at 40% while staying efficient. Bigger picture, this points toward trustworthy world models and controllable video dynamics. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.